regarding how to model state space. Just hold on 1 second. Sorry. Did you understand the concept of how to write the state space equations given that from the differential equations, or depending on whether you have you are given with a transfer function or a signal flow graph? So did you get the concept?
Yes, ma'am.
Okay, so another thing is that, as I must have mentioned, so that since in the state space we will be dealing with, as you have understood, that we will be dealing with mostly the vector matrix. Okay, so we'll be dealing with matrix algebra. We have to do like matrix multiplication, then finding out determinants and all sorts of matrix algebra. Okay, so I would request that you please go through revise your concepts about that matrix algebra, because otherwise it would be difficult for you to solve problems in the state space domain. Okay.
Yes, ma'am.
Okay. So only like mostly the basics are only needed, like let's say the matrix multiplication, then how to find out the rank of a matrix, then inverse of a matrix. Those like the simple matrix algebra is needed. Okay. So today we'll talk about the state variables. So till now we were discussing about the state variables, or how to represent a continuous time system using state space models. Okay, so the state space model, basically it has two equations. So one is the state equation. So the state equation consists of, so it's in the form of x dot is equals to ax plus bu. Okay, where x is basically the state vector, or x is the vector which is formed of the state variables of the system. And on the left hand side you have x dot. So x dot is the first order derivative of each of the state variables. Okay, and you have obviously you have the corresponding effect for the of the input also, so which is given by that bu term. Okay, and the second equation is the output equation. So that output equation is also dependent on, it's also a function of the state variables as well as a function of the input. But in general, the systems that we usually consider, in those kinds of systems, the output is not directly related to the input. So mostly the systems that we would be considering, the value of d, that y equals to cx plus du, that value of d will be equals to 0 in most of the cases. But in case the value of d is not equals to 0, then accordingly you have to write the state equations. Okay, so now we will talk a little bit about the linear, so we'll move on, move ahead, and we'll talk a little bit about the linear discrete time systems. Okay, so a discrete time system, basically it can be like completely discrete with respect to time. That means they will be receiving or sending out discrete signals only. But and the other case which might arise, that is the system might be, the system components might be continuous in time, but the signals which are generated, that are made discrete, the signal which is generated, that is being discretized. Okay, so discretized means that is we are getting the signal at certain predefined intervals. Okay, so that means that even though the basic signal or the actual signal which was coming in is a continuous time signal, but we are actually discretizing the signal using some sample and hold operation, so that at the output we get a pulse kind, or a discrete, we get the signal in the discrete domain. Okay, so in general, if you write the general form of the state model, in case if you have a multivariable discrete time system, so multivariable means the input, there are like multiple inputs to your system. So in that case, you can write the equation, or the general form of the state equation, state model can be written by something like this. So x k plus 1t is a function of xkt, where is xkt is basically the state vector. So state vector means the vector which comprises of all the state variables. Then you have u kt. So u is basically the input vector, y is the output vector. Okay, so what we have done is that we have just discretized the continuous time state equations. Okay, so from this state model, you can say that if you have information about the initial state of the system. So initial state of the system means that you should know the value. Let's say that initial time is t equals to 0. So if you know the value of x0, if you know the value of the state vector at time t equals to 0, and the inputs like u at time 0, t, 2t, so this will be capital T, t, 2t till kt. If these things are known, then what we can do is that we can deduce how the state of the system and how the output of the system can be will be provided. Okay, so that means that, so this is by definition of the state space. So if you know the value, or if you know the information about the initial state of the system, if you know the information about the input of the system till from the initial state till some duration time t, then based upon all those two information, what we can do is that we can predict what will be the nature of the state at a later time instant. So for some value t which is greater than 0, or some value t which is in this case, so for k equals to 1 till k plus 1. So for different time instance, we would be able to find out what will be the value of the state at those time instance, as well as what will be the value of output at those certain time instance. Okay. So now let's write the, so if you have an nth order, let's say you have a linear time invariant system. So linear time invariant system means that, so we can simply write the state equations like kx plus 1 equals to a multiplied by kx plus b into uk. So, and we have defined that x of kt. So in this previous equation, we had a function of kt, the state variable as well as the input variable, they were at time instance kt. So we have just defined x of kt is defined as x of k. So we just substitute it like this, and we write that x at k plus 1th instant will be equals to a multiplied by x at kth instant plus b u of k. And similarly, the output equation can be written like this. From these equations, you can just simply say that, so xk is basically the state vector. So if, since your order of the system is nth order, so that means this xk, this vector will be the dimension of this vector will be n cross 1. Similarly, uk, let's say uk is the input. If you have m number of inputs, so let us say that uk will be the input vector, dimension being m cross 1. Similarly, if you have p number of output variables, then yk will be p cross 1. And this we have already defined earlier. A is known as the system matrix, B is known as the input matrix, C is the output matrix, and D is the transmission matrix. So now if you have, if your transfer function of the system is provided in terms of the Z transfer function, or if you have linear difference equations, then we will see how to write the state equations or the state space model from a differential from a transfer function which is in the form of this Z transfer function. Okay, so if Tz is given by something like this, so you have B0 Z cube plus B1 Z square and so on and so forth. So what we would do is that, first of all, so the highest power of Z in both the numerator and denominator is Z to the power 3. So what we'll do is that we'll divide both the numerator and the denominator by Z to the power 3. So if we do that, then in the numerator we get B0 plus B1 Z inverse plus B2 Z to the power minus 2 and B3 Z to the power minus 3. Similarly, in the denominator we have something like this. So now from here, if you draw the signal flow graph for this system, it will look something like this. Okay, and in the signal flow graph, you see that we have, so U is my input to the system, Y is the output to the system. And we have certain this Z inverse, so these delay elements are present in the system. Okay, so if you remember that when we were talking about a continuous times system, so in that case we said that depending on the number of integrators which are present in the system, output of each integrator will be considered as a state variable. So in a similar way, analogous to that, we can say here that the number of delay elements which are present in this system, that will be equal to the number of state variables. Okay, so here we have like 3 delay elements, and the output of each delay element, that is known as one state variable. Okay, so let's say that the output of this delay element is given by x1, this one for this delay element this is x2, and for this delay element this is x3. Okay, so what you can do here is that you can simply write that if x1, if you write at the kth instant, so x1k, So it is a delay element. So that means this will, the previous one will be plus 1 of the next case. So x1 k plus 1 will be nothing but equals to x2 of k. Similarly, from here you can write x2 k plus 1 is equals to x3 k, right? So this one will be so this is x3 will be equals to x2 k plus 1, and the point over here, this will be x3 k plus 1. Since we are dealing with a delay element, so that means the previous value will, the previous node will be just one order or the value at the previous instant. Okay, so from here you can write the, from the signal flow graph, you can write the different equations. So you have x1 k plus 1 is equals to x2, that we have already written. x2 k plus 1 is equals to x3. And for this x3 k plus 1, you can simply find out what will be the value from the signal flow graph. So that means x3 k plus 1 will be equals to addition of, so this u is coming over here through as 1. So uk with plus, then you will have x3 minus a1 multiplied by x3 minus a2 multiplied by x2 minus a3 multiplied by x1. So we have something like this, right? Similarly, you can write the expression for the output also. So the output is basically y. So y is nothing but this, whatever is the value at this point, that multiplied by this gain 1 will give you y. And the value of the signal or the node at this point will be equals to this gain multiplied by x2 plus this gain multiplied by x3 plus b0 multiplied by, here it will be u only because this is coming as 1, and you have x1 multiplied by this gain. Okay, so you can simply write the equation over here, and once you have written this equation, so you can write this in the form of, so on the left hand side you will have x1 k plus 1, then you will have x2 k plus 1, x3 k plus 1. So this will be your, this matrix will be this. So this you will be equals to some matrix A into, you will have x1k, x2k, x3k, and some b into u. Okay, so from these equations you can simply write, so x1 k plus 1 is only equals to x2, so that means only the second term will be equals to 1. Similarly for x2, only the third term corresponding to x3 is there, so this term will be 1. And for x3, you have minus a3 into x1 minus a2 into x2 minus a1 into x3, plus you will have a contribution for the input. So the third element for B is equals to 1. So from the difference equations, you can simply write the state space representation, where you can find out what will be the value of these matrices A, B, C. And here in this case, the value of D is equals to, so here D is equals to B0. Okay, so this is the form as in the last class we were discussing. So if you can express the matrix A in such a form that the last row is given by the negative of the last row is given by the coefficients of this equation, and all the other rows, the one of, like this is a diagonal or an identity matrix like this. So this is known as the phase variable form or the controllable canonical form of state model. So this is just a type of one form of representation of the state equation. Okay, so you can represent this value of A can be something else also. Okay, so as you remember that this state equations, they are not unique. Okay, but the state variables which are associated with the system, that is unique. Okay, so depending on how your system is connected, you can express this value of A, B, and C. They can be different. So if you have some kind of transformation applied on this value of A, so then if you apply the same kind of transformation for all of these, and keeping that the initial difference equations or the initial equations which were governing the dynamics of your system, those are same, the value of A, B, and C can be different. Okay, but the only thing that remains constant is the state variables, that is the value of x1, x2, x3. In this case we have 3 state variables, so these remains constant, but the value of A, B, C, they can be different depending on how your system is connected and in which form you are expressing your final state space model. So similarly, if you have, let's take another example. So here you have the transfer function in terms of z that is given by this. Okay, so here what we are doing is that we are expressing this in terms of, let's say, as a summation of partial fractions. Okay, so this can be expressed something like this. So you have 1 minus 1 by z plus 1 plus 2 by z plus 2 plus 1 by z plus 3. So you factorize this and you get this equation. Okay, so now if you remember that this is the type of equation which we were seeing when if we want to express the value of A in a diagonal matrix kind of a form. So in this previous case, you see that A is not a diagonal matrix. Okay, so this is some different form of a matrix. But if we want to express A in a diagonal matrix, so that means only the diagonal elements will be there and all the other elements will be equals to 0. For that kind of an expression, what we need to do is that we have to factorize this, or we have to simplify the given transfer function in form of like these separate roots. Okay, so in the denominator we'll have the roots of the denominator polynomial, and accordingly we'll express it in form of a partial fraction form. Okay, so once you express the transfer function in form of this partial fraction, what you can simply do is that you can write the state equation in form of the diagonal canonical state form. Okay, so the diagonal canonical state form says that the state equation, the value of A will have the diagonal elements will be equal to the roots of the denominator polynomial. So here the roots of the denominator polynomial, so z is equals to minus 1, minus 2 and minus 3. So we will have minus 1, minus 2, minus 3 as the diagonal elements, and all the other elements will be equals to 0, right? And similarly, the matrix B will be all one matrix. And in a similar way, you can write what will be the value of yk, and yk will be given by, so these are basically the residues. So this is minus 1, this is plus 2 and this is plus. So these are like, if this is, let's say C1, this is C2, this is C3. So C1 being only this part, okay, minus 1 till 1, C2 is 2 and C3 is 1. So these are the residues at z plus 1, z plus 2 and z plus 3 respectively. So these values will come as the elements in the output matrix. Okay, and this will be expressed in this form. So this is basically known as the diagonal canonical form of the state model. So you see that depending for the same transfer function, you can express the same transfer function in a diagonal canonical form. You can express it in form of that in the previous form, which looks like something like this. So the space variable or controllable canonical form also. So depending on what is your ultimate aim and which kind of expression will be suitable for you, accordingly you have to find the state, or you have to represent the state equations. But in general, you will see that mostly if you express your the state equations in this diagonal canonical form, that becomes much more easier for further analysis. Okay, so now we'll see that if you have been given with the state model in the discrete time domain, so then how to find out the z transfer function from that discrete time domain state model. Okay, so this is the general expression for the state model in the discrete time. So you have xk plus 1 equals to a of xk plus b of uk. So what we'll do here is that we'll simply take the z transform of these two equations. So from the first equation we can write, so if you take the z transform, it will be z into xz minus z into the initial condition x0. On the right hand side you will have axz plus b of uz. Okay, so if you rearrange this equation, you will get xz will be equals to, so on the left hand side you will have from this equation zi minus a into xz will be equals to b of uz my plus z of x0. Okay, so if you just write xz, so this matrix will go to the right hand side and it will be the inverse. So that means you can write that xz will be equals to zi minus a inverse multiplied by this one plus zi minus a inverse multiplied by this. Similarly, for the output equation, you take the Z transform of the output equation. So you get YZ is equals to C into XZ plus D into UZ. So here we are substituting capital D by small t because we are assuming that the output is a scalar quantity. So in case of a scalar quantity, so that capital D will be this vector D is equals to small d. So if so now for the as far as the definition of a transfer function goes, so transfer function basically says that the initial conditions should be 0. Okay, so the initial conditions are 0, so that means this value of x0 should be equals to 0, right? So if you have x0 equals to 0, so that means this term goes to 0. So you are left with only this part, right? So xz is equals to zi minus a inverse b into uz. Okay, so now if you substitute the value of xz in this equation, so you have c multiplied by zi minus a inverse. So this term basically now is equals to 0 because this is equals to 0. So you have c of zi minus a inverse b into uz plus d into uz. Okay, so from here you can write that the transfer function of the system is equals to yz by uz, which is equals to c zi minus a inverse multiplied by b plus d, right? And this zi minus a inverse, this can be written as adjoint of zi minus a divided by this determinant for this matrix zi minus a, and you have c and b previous in the before, and so this will come as multiplication. So you have c multiplied by this inverse of zi minus a multiplied by b. So this is how you can, if you have the state equations in the discrete domain, so then from the state equations what you can do is that you can find out what will be the corresponding value of the transfer function in the corresponding z transfer function. Okay, so if you notice, if this is the transfer function, so that means this is the closed loop transfer function. So that means you can write that the denominator of the closed loop transfer function, that is basically the characteristic equation of my system. So the denominator here is this determinant zi minus a. So we can write from this transfer function that the characteristic equation of the system is given by determinant of zi minus a is equals to 0. Okay, so if you solve this equation, then the roots of the characteristic equation, so if you solve this equation, so the roots of the characteristic equation are basically the eigenvalues of this matrix A. Okay, so you can say that this, if you know the roots of the characteristic equation, so in case of the continuous times domain where we were where we were talking about the root locus and the Routh-Hurwitz criteria, so there we have seen that the roots of the characteristic equation, they are nothing but the closed loop poles of the system. Okay, similarly in this case also you can say that the roots of the characteristic equation are the eigenvalues of the matrix A, and the eigenvalues of the matrix A that will be nothing but the closed loop poles of the system. Okay, so all the conclusions that we had drawn regarding the position of the closed loop poles and the dependence of the stability of the system on the position of the closed loop poles, they will remain valid for the eigenvalues also. So you can say that initially we have seen that if the poles of the closed loop poles of your system, they lie on the left half of the S-plane, then your system is stable. Similarly, for this eigenvalues also you can say that if the eigenvalues, they have negative real values, then the system is stable. But if the eigenvalues of this matrix A, they are like positive values, so that means the closed loop poles of the system, they will lie on the right hand side of the S-plane. So then we can say that the system will not be stable. So depending on the values or depending on the eigenvalues of the matrix A, we can conclude in a similar way about the stability of the system. Okay. So now next what we'll do is that we'll see how to, so we have seen that if you can express the state space model in form, if you can express the state space model in diagonal canonical form, that means where the matrix A is in a diagonal form, that basically helps you do the subsequent analysis much more easily. Okay, so now we'll see how you can make, so if you are given with a transfer, or if you are given with a state model where A, the matrix A is not is a generic one. Okay, so this is not a this is a non-diagonal matrix. So we'll see how we can modify that state equation, and we can come up with a modified version of the state equation where the matrix A is in the diagonal form. Okay, so this process of conversion of a general state model into a diagonal canonical one is known as diagonalization. Okay, so now if you consider an nth order multiple input multiple output system. Okay, so the general state equation will be given by this. So you have x dot is equals to ax plus bu, y is equals to cx plus du. Okay, and here we are assuming that the matrix A, this is a non-diagonal matrix. So our main aim is that we will apply some kind of transformation so that the modified matrix A will become a diagonal matrix. Okay, so for that what we'll do is that let us say that we introduce a different a new state vector. So here the state vector was x, right? So the state vector is equals to x in this one. So now we are introducing a new state vector which is known as v, and this v is related to x by some equation x is equals to m into v, and m is basically an n cross n non-singular constant matrix. So we'll see what is the value of this matrix M in some time. So if you do this kind of a transformation, then what we'll find is that, so here you will get, so from this one you will get that x dot will be equals to nothing but M multiplied by V dot will be equals to A M into V plus BU, right? So we'll simply substitute these, okay? And similarly Y will be equals to C M into V plus du, right? So if you just divide both the sides with this matrix M, so you will get V dot is equals to M inverse AM into V plus M inverse B into U, and Y will be equals to, Y will remain the same, CMV plus DU. Okay, so now if you want to express this state equation in this form, so you have V dot will be equals to some matrix delta. Okay, so some matrix delta plus some matrix B bar into U. Okay, so you can write that this matrix delta is nothing but that it will be equals to M inverse A into M. Okay, so now if you can select the value of M in such a way that our main aim is that this matrix, this delta should be a diagonal matrix. Okay, so if you can select the value of M in such a way that M inverse A of M, that is a diagonalized matrix A, so that means this delta will be a diagonal matrix. Will be a diagonal matrix. Then this state equation will be in the form of the diagonal canonical form. Right, so because now after this, so you have to choose this value of M in such a way that M inverse A into M, this value of this matrix, that is a diagonal matrix. Okay, so from here we can say that M is basically defined as the diagonalizing matrix, or you can say M is known as the modal matrix. Okay, and the value of this the effect of this modal matrix is such that it actually, if you do this kind of a transformation, if you do M inverse, if you take the value of M inverse A into M, so that becomes equal to our diagonal matrix, which is a diagonalized form of the matrix, original matrix A that we had. Okay, so we can write that delta is equals to M inverse AM. Similarly, B is equals to M inverse B, and the modified C is equals to C into M. Okay, so if you want to transform this one matrix, transform a non-diagonal matrix into a diagonal one, so what you need to do is that you have to find out what will be the value of this matrix M. Okay, M, or which is the diagonalizing or the modal matrix. Now, before we move, in order to, you can say that the determination of this diagonalizing matrix, that is the matrix M, that is basically dependent on, or that is useful, or that is easy if you know what will be the values of the eigenvectors of the matrix A. Okay, so we'll just recap a little bit about the eigenvalues and eigenvectors. Okay, so just because these are like these eigenvalues, finding the eigenvalues of a matrix is very important, because it's important because if you depending on the values of this eigenvalues of the matrix, you can infer whether the system will be a stable system, or you can talk about how the response of the system will look like, whether the system is an overdamped system, underdamped system. All the inferences which we had done, or which we had concluded for closed loop poles. So the same things can be concluded if you can find out the eigenvalues of the state model. Okay. So now let's say that let us take this equation Ax is equals to y. Okay. So from this equation you can say that the transformation, so this is the vector x, so this is an n cross 1 vector. So this n cross 1 vector is transformed to a vector y, which is an n cross and this transformation is done by this matrix A, which is an n cross n matrix. Okay, so if both x and y are n cross 1 vectors, then A will be a n cross n matrix operator for this kind of a transformation. So now the question which arises is that whether there exists a vector x such that if you do this using this matrix operator A, such that the matrix operator A, it transforms this vector x into a different vector which is given by lambda x, while lambda is basically a constant, and the main aim is that this transformed vector, this lambda x, is having the same direction in the state space as the initial vector x. Okay, if this question, or if the answer to this question is yes, then we can say that such a vector is basically a solution to this equation. So Ax will be equals to y. The solution of this one will be a vector Ax is equals to lambda x, provided that this lambda x is a vector which has the same direction as the initial vector x in the state space. Okay, so from this equation you can write that, you can just simplify, or you can just rearrange this equation, and you can write, so lambda I minus a into x will be equals to 0. Okay, so and this equation, this lambda I minus a multiplied by x is equals to 0, this equation will have a set of homogeneous equations, and this will have, so this is, since this x, the value of x is a vector, so that means this is a set of equations. Okay, so if you want to solve this set of equations, so this set of equations will have a non-trivial solution if and only if the determinant of lambda I minus a is equals to 0. If this condition is satisfied, that is the determinant value of lambda I minus a is equals to 0, which is nothing but the characteristic equation of the system, then this equation will have a non-trivial solution. Okay, and this equation can be, you can expand this characteristic equation in a polynomial form, and you can write it in this form. So q lambda will be equals to lambda to the power n plus a1 lambda to the power n minus 1 till an. Okay, so this is the expanded form of the characteristic equation, and the general form of the characteristic equation which is for a system whose state space model is provided. For that, the characteristic equation is given by determinant of lambda I minus a is equals to 0. Okay, so now the value of lambda for which this equation is satisfied. So if you solve this equation, so you will get n number of values of lambda. Okay, so the values of lambda for which this characteristic equation is satisfied, they are known as the eigenvalues of this matrix A. Okay, and we already know that the roots of the characteristic equation, or the solution of the characteristic equation, are nothing but the poles of the closed loop transfer function, or the poles of the closed loop system. So we can say that by comparing these two statements, we can say that the eigenvalues of the state model, that is the eigenvalues of the matrix A, and the poles of the closed loop transfer function, they are the same. Okay, so we can say that if the eigenvalues, they have negative real parts, so that means the system will be stable, right? So now next, let us say that the value of lambda is equals to lambda I. It satisfies the characteristic equation lambda I minus a equals to 0, right? Because we have solved this equation lambda I minus a is equals to 0, and we have found out that the solution for those equations are lambda 1, lambda 2 till, let's say, lambda n, because it was an nth order equation. Okay, so if you let us take one value of this lambda, so let's say that value is lambda I. So we can simply put the value of lambda I in the previous equation. So the actual equation that we had was lambda I minus a multiplied by x is equals to 0. So we substitute the value of lambda I. So lambda I multiplied by I minus a into x will be now equals to 0. Okay, so now if you solve this equation, let us say that one solution of this equation is x equals to mi. Okay, and mi will be known as, so if you can find the solution of this equation in form of x equals to mi, then this is known as the eigenvector of the matrix A, which is associated with the eigenvalue lambda I. So you can say that corresponding to each value of lambda or corresponding to each eigenvalue of your of the matrix A, you will have one eigenvector which is given by mi. Okay, and the solution for this equation, the solution of lambda I into I minus a into x is equals to 0, it basically depends on the rank of this matrix lambda I minus a. So if you know the rank of this matrix, so if the rank of that matrix is R, then there will be n minus R independent solutions. So that means there will be n minus R eigenvectors of the equation. And if all the eigenvalues of the matrix A, they are all distinct, so that means they are separate, all the eigenvalues have distinct separate values, then the rank of the matrix lambda I minus a is nothing but n minus 1. So you can say that only one independent eigenvector is present corresponding to each value of lambda I. So you will have, for corresponding to each value of lambda I, so if you have n number of eigenvalues in your system, you will have n number of eigenvectors in the system. Okay, and so that and how to find out the value of this eigenvector mi? So eigenvalues you can find out simply by solving this equation that lambda I. So we have seen that if you solve this equation, lambda I, determinant of lambda I minus a is equals to 0, you can find out what will be the value of the eigenvalues. Okay, and from the eigenvalues you can find out the eigenvectors using this equation. So eigenvectors are basically can be found out by taking the cofactors of the matrix lambda I minus a along one row. Okay, so the cofactor, basically if you see the cofactor, so if the matrix given to you is Aij, where I is basically the row and j corresponds to the column, then the cofactor, if cofactor Cij, so Cij will be equals to minus 1 to the power I plus j into determinant of the minor ij. Okay, so from here you can find out what will be the value of the eigenvectors. So mi will be equals to ck of 1, ck of 2 till ck of n, where the value of k varies from 1 to till n, and cki are basically the cofactors of this matrix lambda I minus a. Okay. Now, so obviously now since we have n number of eigenvalues in our system, so we'll have n number of eigenvectors. So let us say that all the eigenvectors are m1, m2 till mn. Okay. So now if we write this equation, so if we write this matrix A of m, so this matrix M is equals to, can be the modal matrix or the diagonalizing matrix M will be equals to A multiplied by this m1 then m2 till mn. If you take this matrix A into inside the matrix, so you will have A of m1, A of m2 till A of mn. And since this was the solution for so x was equals to mi, so you can simply write you can simply express this in terms of lambda in terms of the eigenvalues. So a m1 will be equals to lambda 1 into m1, a m2 will be equals to lambda 2 into m2 till lambda n into mn. So now you can write, you can sort of expand or you can separate out this matrix and you can write it in form of m multiplied by this vector delta, where this delta is basically this diagonal matrix where the elements, the diagonal elements are nothing but the eigenvalues of the matrix A that we have. And we already know that the value of delta is equals to m inverse A into m. Okay, so then we can say that the matrix which is constructed by placing the eigenvectors together is the, so this M matrix is nothing but the, if you take the eigenvectors and you place the eigenvectors together and you form the matrix, that will be equals to the final or the diagonalizing or the modal matrix of the overall system. So you can find out what will be the value of this modal matrix by finding out this eigenvectors of the system. And once you have found out the eigenvectors of the system, you can simply find out what will be the value of this lambda. Or from here, actually, you can find out the value of lambda can be found out simply from the eigenvalues. But if you want to find the other, like the modified B vector or the modified C vector, in that case, you need to know what will be the value of this modal matrix M, because we have seen that C, the modified C is equals to C into M and modified B was equals to M inverse into B. So we need to know the value of M in order to find out what will be the modified output matrix as well as the input matrix. Okay. So this will become a little bit more clear. So that was the concept of how to find out what is the eigenvectors of your system. Now let us do an example, then things will be much more clear. Okay, so let's say that if you have been given with an equation, the state equation is given such that the value of this matrix A is given by this. Okay, and what you have to do is that you have to find out what is the value of the modal matrix. You have, so this is a matrix which is not in a diagonal form. So this is a non-diagonal matrix. Okay, so what we need to do is that by using that modal matrix, we can transform this non-diagonal matrix into a diagonal one. Okay, so you have to find out what will be the value of that modal matrix. So the first thing that you need to do is that you have to write the characteristic equation, and the characteristic equation is given by lambda I minus A is equals to 0. So you can simply write lambda I minus A will be expressed as this, because lambda I is nothing but lambda 0 0 0 lambda 0 0 0 lambda. Right, I is an identity matrix and you multiply with lambda, so you'll get this. So lambda I minus A will give you this equation. Okay, so from this equation, if you take the determinant and equate it to 0, you can find out what will be the value of the lambda. Okay, so if you write the simplify this equation, you will get that this is how these are the solutions for this equation. So you have three solutions. So you have lambda 1, which is equals to minus 1, lambda 2 is equals to minus 2, and lambda n, or not lambda n, lambda 3 is equals to minus 3. Okay, so we have found out what will be the value of the lambda. So if you want to write that the diagonal, the modified matrix, so this modified matrix will be equals to lambda 1, then 0 0, then 0, lambda 2, which is minus 2 0, then you'll have 0 0 and minus 3. So this will be the modified or the state matrix in the diagonal form. So the form was V dot was equals to lambda x plus B bar into U. Okay, so here this value of delta is given by this. But now you need to find out what is the value of the modal matrix. Okay, so for finding out the modal matrix, what we need to do is that we have to find out the individual eigenvectors. And once we know the individual eigenvectors, we can simply substitute the eigenvectors in the, so this will be eigenvector M1, this will be M2, this will be M3. So accordingly, you will just substitute these values and you will end up with the final modal matrix. Okay, so for finding this eigenvector, so as we have already told that corresponding to each eigenvalue, we will have one eigenvector. Okay, so that means we have three eigenvalues over here. So that means we will have three eigenvectors, and then those three eigenvectors will be arranged in this way in order to find out the modal matrix. And the eigenvector, so corresponding to lambda 1 is equals to -1, you can write that lambda 1 I minus A will be given by this matrix. And once you have found this matrix, so from this one you can find out what will, if you take the cofactors of this matrix, then you can find out what will be the value of M1. So for the first element you will have C11, which will, so we will remove these two and we'll take, so this is the minor, so we'll have -1 to the power I plus j is equals to 1 plus 1, 2 multiplied by the minor of this one. So that will give you 9. Similarly, you can find out for the other cofactors. And here you can write in the simplified form, the matrix M1 is given by the eigenvector M1 is given by 1, -1, and it's a column matrix, the elements being 1, -1 and -1. In a similar way, you can find M2. For this M2, what we'll do is that you will write this equation lambda 2I minus A. Okay, you write this equation and you write this matrix, and from this matrix you find out what, you take the cofactors of this matrix and you find out what will be the value of the second eigenvector. Similarly, you can find out the value of the third eigenvector also. So once you know the value of M1, M2 and M3, you simply substitute those values in this row form and you will end up with the modal matrix. So M is basically the diagonalizing matrix or the modal matrix, such that if you do M inverse A into M, that will give you, that will be equals to this delta. So you can verify, you can cross check, take this value of M, do M inverse A into M, you cross check and you see whether you are ending up with this form or not. So this is like to cross check whether the modal matrix that you have found out, that is correct or not. If there is some, in case if there is some error, so that means that this equation will not be satisfied. If you have done your calculations correctly, then M inverse A into M, the product of this matrix multiplication will give you the matrix delta, which is given by this, the diagonal elements being the eigenvalues of the matrix A. Okay, so is it clear till now?
Yes, ma'am.
Okay, so the main thing here is that you have to know how to find out the eigenvalues of from the state equations, how to find out the eigenvalues of your system. Okay, once you know the eigenvalues of the system, you can do some from the eigenvalues you can find out what will be the corresponding eigenvectors, and from the eigenvectors you can write what will be the modal matrix or the diagonalizing matrix, which diagonalizing matrix means that is the transformation which is applied to the original state equation, such that the modified equation is in the form of a diagonal canonical form. Okay, so next we'll talk about, so now why do we need to first of all, so the state equations, this vector algebra and all those things, so like what is the ultimate aim? So first of all, we had already talked about that these kind of state space equation, the analysis of a system using state space equation, that is that you can say is much more easier if you are dealing with a much more complex system. Okay, so much more complex system means if you have multiple inputs to your system and the interconnections in your system are too complex, and if the order of the system is very high, let's say you have a fourth order, fifth order system. So in that kind of a scenario, if you express or if you model the system using the state space equations, then it becomes easier for you to further analyze. Further analyze means if you want to find out what will be to study the transient response, the time response of the system, to study the frequency response of the system. So those kind of systems, like complex systems, studying the transient analysis or the frequency response analysis, these things become much more easier if you have the state equation, if you know the concept of state equation, and if you can model your equation or you can model the system using state space equations. Okay, so now we'll see about how, so what will be a solution for this state equation. So the solution for the state equation basically will give you the system transient response. Okay, so you can say that the system transient response that can be found out by solving the state equations. Okay, so the state equations basically we have x dot is equals to ax plus bu. So this is my state equation. So if you solve this state equation, you will get what will be the system transient response. So before we start that, so let us take a very simple first order derivative, and this is a scalar quantity. So now here we are dealing with x, which is not a vector but a scalar quantity. Okay, so if you try to do the solution for dx dt is equals to ax, this equation, given that the value of x0 is equals to x at time t equals to 0 is equals to x0. So this solution can be written as xt is equals to e to the power at multiplied by x0. Okay, and you can expand e to the power at and you can write it in this form. So this is 1 plus at plus 1 by 2 factorial a square t square and so on and so forth. Okay, so now, so this is for the scalar quantity. So basically x is a scalar quantity here. So for that the solution of dx dt is given by this equation. Okay, so this equation is similar to this one. You can write that this is very similar to x dot is equals to a into x, right? So this is similar to the state equation, right? Here also we have x dot is equals to capital A, where A is a matrix. Now since we are dealing with the vectors, so that means these scalar quantities will be substituted with vectors, and the scalar quantity A will be now substituted by a matrix A, and then you will have other variables B, U. Okay, so initially first let's consider the state equation x dot is equals to a of xt. So this is, so we don't have this component u, component corresponding to u. Okay, so this basically represents a homogeneous linear unforced system. Unforced system means we are not providing any external input to the system. Okay, so this system will have the value of ut is equals to 0. So that means we can write x dot t will be equals to a of xt, and the value of this vector x, the state vector x at time t equals to 0 is given by this x0. Okay, so now if you like analogous to this scalar case, so we can assume that the solution for this equation will be something in this form. So we will have a0 plus a1 into t plus a2 into t square till some an. Okay, and ai are basically the vector coefficients. Now we'll see what will be the value of these a0, a1 and these values. Okay, so now once we have assumed this equation, so we can simply substitute the value of xt in this equation. We can take a derivative. So x dot t here will be equals to a1 plus 2 a2 into t plus here we'll have ai into t to the power I minus 1 plus so on and so forth. Okay, so from here we can simply, so x dot is this. So on the right hand side we will have that is equals to a into, so we'll have a0 plus a1t plus we'll have ai t to the power I plus this. So if you substitute this value of xt in the state equation that is provided, you will end up with this equation, right? So now if from this equation, if you compare the equal powers of t on both the sides, so you can write that the value of a1 will be equals to a into a0. Similarly, a2 will be equals to half of a into a1, and a1 if you substitute this, so it will be 1 by 2 factorial a square into a0. Similarly, ai will be equals to 1 by 1 factorial a to the power I into a0, right? So, and if you assume that at t equals to t0, it is given that at t equals to t0, the value of x0 is equals to x0. So we can simply write from here that x of 0 will be equals to a0. So all these terms becomes equals to 0. So this is nothing but x0, right? So now in this equation, what we'll do is that in the solution, we will simply substitute the values of A1, A2 and all this A0, A1, A2 till AI, and we'll find out what will be the final solution. So you have xt. So xt will be equals to x0 plus, so or rather you can write, so xt will be equals to, here we have seen A0 plus A1 into t. So xt will be equals to A0 plus A1 is A into A0 into t plus A2 is half of or 1 by 2 factorial A square into A0 into t square plus so on and so forth. Okay, and if you and A0 is nothing but equals to x0, so you can substitute A0 by x0. Okay, so from here you can, if you take this x0 outside, you can write that the value of xt will be equals to I plus A into t plus 1 by 2 factorial A square t square and so on and so forth. And this equation is basically, and you see that each term, so this I is also an n cross n matrix. The value of A is also an n cross n matrix. A square is also an n cross n matrix. So all the terms in the bracket, they are all individual n cross n matrix. And this whole term, this I plus AT plus 1 by 2 factorial A square t square, if you see that this is in the form of this e to the power at. So when we were talking about a scalar quantity, scalar value of A, so this was given by 1 plus at plus 1 by 2 factorial A square t square. So that equation and this equation are in the similar form. So you can just write that e to the power A, where A is the matrix A, e to the power at is equals to I plus at plus 1 by 2 factorial A square t square, so on and so forth. So the solution to the state equation now becomes xt is equals to e to the power at multiplied by x0. Okay, and this e to the power at basically is known as something which is known as state transition matrix. Okay, so we'll talk more about this state transition matrix in the next class. So this solution is basically the transient response of the system. Okay, so we'll continue talking about how we'll solve a few examples, and we'll see how this solution of the state equations are coming in the next class. So one thing that I would want to say here is that next week we'll have the quiz for module 3. Okay, so the exact date of the quiz I'll probably announce by next Monday or Tuesday. So we'll have at the later end, so probably by Thursday or Friday we will have the quiz. So the date and time, those things I will inform you later on, but there will be a quiz next week. That is one thing. And the second thing is that next week also Tuesday I need an extra class. Okay, so I'm taking a few extra classes because the syllabus is quite large, and if I can finish it before, then I'll probably skip the last classes, or we can have some discussion in the last few classes in case if you have some doubts. We can solve some problems, and then it would be easier for you. Okay, so next Tuesday again we'll have a class from 2:30 to 3:30, and this week obviously we don't have any more classes because tomorrow and day after tomorrow are holiday. So yeah, so that's all from my side today. So in case if you have any doubts, you can ask.
Ma'am, actually, I wanted to ask a query, ma'am.
Yes.
Ma'am, actually, I'm not able to I read for quiz second very good, very proper, in a very proper way, ma'am, but I'm not able to solve the level of the questions which are coming in quiz, ma'am. I don't know. I'm feeling the paper is very lengthy. And
paper is lengthy. Yes, I can say why the paper is lengthy, because since we are mostly, so this is like see, the question paper is set by both me and the other faculty who is taking for the section B. Okay, so it's like a combined question paper. So the main aim is that since we are giving you like MCQ kind of a question, that's why we are making the questions a little bit more lengthy. But since mostly I'm not sure, but your end semester is going to be an offline exam. So probably during that time things won't be that much lengthy, because anyways you will have to write it on pen and paper, and it won't be of probably it won't be of an MCQ type. Okay. So lengthy question paper, I agree that questions are lengthy, but do you feel that the questions are difficult for you to solve? Given a certain amount of time, how do you feel about the difficulty level of the questions?
Ma'am, like the questions are not difficult, ma'am, but it's like it's taking a long time to solve them, ma'am.
Okay.
Specifically the
Many
block.
questions we are unable to attempt also. At last, we just try to take down only
Okay,
because we are
so
unable to
maybe at
solve.
the end, if you are unable to solve, you're just randomly selecting some values.
Yeah, because ma'am, there's no time left to solve. Already
Okay.
there are multiple questions, and ma'am, there are multiple questions in which there are a lot of calculation and it's too lengthy. So we are unable to solve the rest of the questions.
Okay. Okay, fine. So okay, fine. So what I'll do is that let me discuss with the other faculty, and then let's see whether we can make the questions a little bit shorter in length so that you get sufficient time to solve all the questions.
Ma'am, can you suggest something, ma'am, like how to proceed now? Because how to practice? Because at the practice level, I guess I'm getting this, ma'am. Because you are setting the questions are easy, ma'am, but it's taking too long. So how to cut the time? We will also try from our end how to cut short that time. And ma'am, you're also trying to help us, ma'am. So
Yes, so the only thing about like how to like improve the speed, so all I can say is that you have to practice more. So I have already I'm trying to give you more and more practice problems, because see, control theory is basically, there is concept obviously, but this is based mostly on mathematics. Okay, so mostly whatever problems that we are saying, you see that they only have mathematics involved in them, right? So you have to know the basics, and you have to solve the equations and then find out whatever is given. Okay, so the only thing that you can do to improve your speed is that you try to solve practice little bit more. That's the only thing that I can say. And since you're saying that understanding the questions and trying to solve the questions, that is not a big problem for you, as far as I understood, that the questions are okay, but it's just that the time is getting shorter.
yes, ma'am. Like for a question, like I did your example questions, ma'am. What you gave in module 2, and I was able to do it, ma'am. But in the quiz, what happened, ma'am? Like for a block diagram to solve, I was taking a long time, and same for signal flow graph, ma'am. Like for
Okay.
20 minutes, I'm taking for one question, ma'am. So because of that,
Okay.
I was not able to do more questions, ma'am, and the time was limited for 1 hour. I was able to solve 3 to 4 questions on my own, ma'am. Then afterwards, I had to randomly tick the
Randomly, yeah.
submit the question, ma'am.
Okay. Okay, so I get your point. So I'll try to give, at least from my side, I'll try to give you problems which will take less time. I cannot guarantee about what the other faculty would be doing, because he also might be having his own thoughts, right? So I'll try to discuss with him so that we can maybe reduce the length of the paper a little bit, so that it becomes easier for you to solve at least majority of the questions.
Yes, ma'am. Thank you, ma'am.
Okay, so I'll try to do that.
Yes, ma'am. Thank you, ma'am.
Okay. Thank you, everyone.